All right. So section 16.3, the autoionization of water. Anybody know what auto means? Yeah, self. Yeah, auto typically means self, especially when in like as a prefix for science stuff. So autoionization means it's essentially ionizing itself. So in pure water, the following equilibrium is established, and they give us this equation here: two water molecules, and they go back and forth between being two water molecules and a hydronium ion and a hydroxide ion. Okay. This process is called the autoionization of water. All right, now um, there's this uh, there's this what's called an ion product constant, the Kw. Okay, now what I've done here is I've put in the sort of like variables for the different parts of this. So like the lowercase, I don't know, can you guys see it? Yeah. The lowercase a's, the a, b, and c are the coefficients. The capital A, B, and C are the compounds or the ions, the substances. And then from this, you can get your ion product constant plugging the stuff in this way. Okay. So what ends up happening, oops, sorry, is so if you ever have something that's different, like you can use that to get it. Now, water, um, so with water, you can actually do this sort of, I don't know if it's neat or weird or what you want to call it, but um, you can set it up to be essentially when they do it in brackets like this is the concentration. Brackets refer to concentration. So it's like the concentration of hydronium times the concentration of hydroxide is your Kw constant, which is also the Kc, which is what we were just looking at with the, yeah, I don't know what I just did with that paper, but yeah, this deal. Okay, so, all right. At 25 degrees Celsius, the ion product of water is 1.0 times 10 to the negative 14th. Okay, now, and we'll get into this a little bit, but if you guys know anything about pH scale runs 0 to 14. So that actually, some of that comes from this. Okay, so the concentration of hydronium times the concentration of hydroxide will equal this, always, for autoionization of water. Okay, so we've got some things down here to kind of remember. If the concentration of hydroxide equals the concentration of hydronium, if they're the same, then it's neutral. No, if the concentrations, like in this thing right here, like in this, it would be on one side of this, sort of. So like, okay, let me back up a second here. So basically what this equation is saying is, so imagine you've got pure water, right? Pure water can exist as water molecules, H2O. It can also technically exist as a combination of hydronium and hydroxide. If you have equal amounts, essentially they balance each other out and you're neutral, which is like what pure water is. So like think about like atoms. You know how we talked about like electrons and protons, and if they balance out, it's neutral. Like there's no charge. That's kind of like this. Like you could have hydronium and hydroxide, but if you have equal amounts of each, then it's balanced and neutral. Does that help a little? Someone?
How do you know that they're balanced?
Oh, it would have to. They would either have to tell you, or you would see the numbers. Like, so basically, that's what this is. Uh, so what I've done here is, so they would either have to tell you that it's neutral, or they would give you like one of them. So that's what this is actually figuring out. If if this is the total kW, the one times 10 to the negative 14th, equals your hydronium times your hydroxide, right? If they're the same, what I did here is I just put x's over them to give you guys the idea that they're the same thing. Like if they were both x.
Yeah.
So you have x times x, right? Which is essentially x squared. So if you take the square root of that, because they're the same thing, times itself, you take the square root. So you take the square root of this, you get 1 times 10 to the negative 7th. And then this is molar, because it's a concentration. This could be molar too, actually. Or, I don't know if that's molar or not. I'm trying to think how that would work, because there's actually two of them. Um, so if either of them is this number, 1 times 10 to the negative 7th, then it's neutral. Because then the other one has to be the same thing because they have to equal this. So, but like I said, they'll either have to tell you they're neutral or they'll give you the number for one of these that is that number. And then when you see that number, you just automatically know it's neutral. Okay. And then look at these here. If there's more hydronium than there is hydroxide, it's acidic because the hydronium is like the H plus, right? So just think of it like a balance. If you've got the same amount of hydronium and hydroxide, it's neutral. If you've got more of the hydronium and less of the hydroxide, it's acidic. If it's flipped the other way, if you've got more hydroxide and less hydronium, then it's basic because the negative is basic and the positive would make it acidic. Does that feel like it makes sense, at least so far in words? Okay, let's take a look at, I think, and it becomes easier kind of, I think, when you see the problems, to be honest. Okay, let's take a look at this, the calculating hydrogen from pure water one. Okay, so calculate the values of H plus. Remember, this same exact, you can swap it, interchange it with H3O plus, same thing. So anywhere that you see an H3O plus, you can put H plus instead. So if they're asking for H plus, it's the same thing as asking for H3O plus, and vice versa. You can swap them, interchange them with no problems, okay? Calculate the values of H plus and OH negative in a neutral solution at 25 degrees Celsius. Okay, so it's a neutral solution, right? So all we have is there's really, to be honest, there's no calculating anything. That's that's actually the math that I already did. I guess I could have just waited on the math. That's this. So if you already put the math on the other one, I guess you have it. I didn't realize I did that. Those are old notes. So this is the combination, right, of H plus times the concentration of OH minus. If it's neutral, that tells us that H plus has to equal OH minus. So that means they're the same thing. So basically, if we do, let's say h plus, it would be squared. And then you take the square root of both sides. And that's when we end up with the 1.0 times 10 to the negative 7th molar is the H plus. And then hydroxide has to be the same, so 1.0 times 10 to the negative 7th molar is the OH minus. Okay, so that's what I just talked through before on the notes. I don't know why I had it on there twice, but it is what it is. Okay. All right, let's take a look at the second part. Indicate whether the solutions with each of the following ion concentrations are neutral, acidic, or basic. So remember, they have to essentially combine to equal 1 times 10 to the negative 14th, right? So like if we look at number 1 here, I'll kind of show you the math behind it, and then once you get used to it, you don't even have to do the math because you'll see the way that it works. So like for number 1 here, we've got the 1.0 times 10 to the negative 14th equals, and then this is the hydrogen, which is this, right? 4 times 10 to the negative ninth times the hydroxide. So all I'm doing is I'm using this right here, and I'm substituting in the hydrogen that they gave us. Everybody good with that so far? Okay. Then you just solve this. So you would divide, and well, there is a 4 there, so let's see. So this comes out to be, God, mental math, 2.5 times 10 to the 1, 2, 3, 4, 5, 6, negative 6 equals, that's molarity, OH negative. So now remember what I was saying here. If the hydronium concentration or hydrogen concentration is greater, it's acidic. If the hydroxide concentration is greater, it's basic. So this one would be, which one is greater? You got to be careful because of the negatives and the exponents. So technically, which one would be greater? The hydrogen or the hydroxide? I think, yeah, hydroxide. Hydroxide is greater. So number 1 is going to be basic. What about 2? So it's neutral, acidic, or basic? Yeah, good. Neutral, right? Because it's 1 times 10 to the negative 7th, automatically neutral. No work necessary. Okay. Now, what do you think about 7 times 10 to the negative 13th? So let me ask you guys this. Do you think that this is going to be, like the concentration for this is going to be bigger or smaller than the other one? Smaller, right? Because it's out of 10 to the negative 14th, you've got, I mean, it doesn't, like if you look essentially, like, yeah, the numbers are in front, so if it's close, you might have to do the math, but really look at the numbers, right? Like that one was smaller, this was bigger, this is smaller. I mean, you can do the math if you want, but that's what you're going to end up seeing. This is now make sure you know which one you're looking at if it's hydroxide or hydrogen, right? So yep, we end up with essentially 1.4 times 10 to the what is that, -2 molar for the hydrogen. So you guys are right. This is smaller. Hydrogen is bigger, which makes it what? Acidic, basic, or neutral? Acidic. Yeah, hydrogen is stronger, is bigger, so acidic. Good. Okay, so calculating hydrogen concentration from hydroxide. So calculate the concentration of hydrogen aqueous in a solution in which hydroxide is 0.010 molar. Okay. Now, this in reality, this is really the same thing you were just doing, except instead of saying like acidic or basic, which we could still do, you're just calculating it out. So our equation is hydrogen, concentration of hydrogen times the concentration of hydroxide equals 1.0 times 10 to the -14th. Um, and we plug in the hydroxide. So these look kind of complicated, but in reality, they're really relatively simple. These at least are relatively simple algebraic problems. So you just take this divided by that, and we get a hydrogen concentration of 1 times 10 to the -12 molar. Okay. Now, you could, if you were asked, you could tell if this were acidic or basic, right? Which one would it be? Yeah, good. Because the hydrogen's a lot smaller than the hydroxide, right? So if it asked you, you could be able to tell that it was basic. Okay. Okay, let's take a look at part B. A solution in which hydroxide is 1.8 times 10 to the -9th molar. Um, Assume, unless stated otherwise, that the temperature is 25 degrees Celsius. That goes for all of these. Unless it states otherwise, it's 25 degrees Celsius, which is what the equilibrium works at. So this is really just the same type of deal, right? All right, so we get something like 5.6 times 10 to the -6th, right? double check my math. Is that what some of you guys got? Yes, molar. Okay. So would this one be acidic or basic? Good, acidic. All right.